In this video, we are going to derive the conditional variance of the slope estimator in the simple linear regression model. That's a really fancy title, but it's really not complicated. So what we want to check is what is var of beta 1 hat, so that the slope estimator, conditional on x. So for this, we are going to start with the second form of the slope estimator, which is beta 1 plus sum of xi minus x bar times ui over sum of xi minus x bar square. If you don't remember where this formula comes from, just go and check the video about the unbiasedness of the slope estimator. It's the first thing we derived. So now I'm going to rewrite that as the variance, and then beta 1 is a constant, so we can just remove it, right? The variance of something plus a constant, we can just remove the constant. I'm going to take the sum of the squares at the bottom and put it in the front. Sum of xi minus x bar square times sum of xi minus x bar ui. So we are going to use a rule that says variance of ax is equal of to a square variance of x, and we are going to apply this to the sum of the x squares here. Because it's conditional in x, we can take it out. It's like it's a constant, and we have sum of square xi minus x bar square, and the whole thing here is squared, times the variance of the sum of xi minus x bar ui conditional on x. Now we are going to use another rule that says that the variance of a sum is a sum of the variance if the elements of the sum are linearly independent. Here we can say that the elements are linearly independent, not correlated, because we have independent rows. We have a random sample. So this is equal to 1 over the sum of xi minus x bar square times the sum of the variances xi minus x bar ui conditional in x. Again, because we conditioned on x, xi minus x bar is a constant, we can take it out of the variance and square it. So first, let me rewrite the first term in a more simple form, xi minus x bar square, and I'm going to keep the square just at the bottom because at the top 1 squared is just 1. Sum of the variances, so sum of xi minus x bar variance of ui conditional on x. And this is the first time we are going to use SLR5, which is that the variance of the ui conditional on x is constant and it's equal to sigma square. We did not need it to prove the unbiasedness of the estimator. We just need it to find the variance. So, oh, I forgot the squared here. So be careful. xi minus x bar, when you take it out of the variance, you have to square it. So I'm going to rewrite this 1 over the sum of xi minus x bar squared, the whole thing squared, sum of xi minus x bar square, sigma square. Now, in the sum, sigma square is a constant, so I can take it out of the sum, and I get 1 over the sum of xi minus x bar squared times sigma square sum of xi minus x bar square. Now we see that we have the sum of xi minus x bar squared at the top and at the bottom of a division. Here it's squared, so I can simplify it. I will remove the square here and remove the term at the top. So I get sigma square over sum of xi minus x bar square. So this concludes the proof. Note that this is not equal to the unconditional variance of beta 1 hat, because here we have something that depends on x's, and if we uncondition, we will have to take the expectation over x, and that gives a much more complicated formula. That's all for the second tutorial for this course. Don't forget to like, subscribe, and share with everybody, even if they don't know anything about econometrics. See you next week.